Alright, so in this video we are going to be talking about carbon, nitrogen, and oxygen nucleophiles, and the reactions that we'll be doing involve ketones and aldehydes. More like aldehydes and spirit because we'll be doing mostly ketones, but the idea is that it's just a replacement of a carbon group and a hydrogen group. So to start, let's start talking about how carbonyl groups react with their environment. So because the carbonyl groups can serve as, because carbonyl groups can undergo nucleophilic attacks, this happens because the carbonyl basically has an oxygen, and this oxygen is more electronegative than the carbon it's attached to, and this gives the molecule a dipole moment, meaning that the oxygen is more negative than the carbon. And this also means that our nucleophiles will attack the carbonyl groups from the back, moving the electrons up to the oxygen, and this forms an unstable oxygen group, meaning that it's now negative. So to stabilize that, the oxygen will undergo a proton transfer reaction, making the oxygen into a alcohol group. Reversely, kind of like I just explained, the oxygen can also attack an electrophile because it has these electrons on it, and so it's, I would say, like, technically more negative than the group is trying to attack. So these electrons will transfer over to the electrophile, forming that bond and making that oxygen more positive because it has an extra bond. So to stabilize this molecule, the electrons will be moved up from this double bond here to the oxygen, giving the oxygen a stable charge. Alright, so first, I think it's important to talk about carbon nucleophiles. All of our carbon nucleophiles will be written in this video in blue, so it's easy to tell what's what. So I think let's do nucleophilic addition first. We'll start with a standard carbonyl group, double bonded to an oxygen. This is our carbon that our nucleophile is going to attack. And essentially, we have our nucleophile, the carbon triple bonded to carbon to a hydrogen group. This nucleophile is negatively charged, and it's going to attack the positive dipole moment in comparison to the negative dipole moment on the oxygen. So this nucleophile will attack the carbonyl group from the back, moving the electrons up to the oxygen, and this will form an unstable oxygen atom because it's now negative instead of neutral. So we will do a proton transfer step, and we'll use a hydronium ion. You could also use a water molecule. So the electrons from the oxygen will grab a hydrogen. The hydrogen will lose its electrons, and those will go back to the oxygen on the hydronium ion, and then we will have an alcohol group attached to our nucleophile on the same carbon. Okay. Next, let's start talking about ylids. So this below is an ylid reaction mechanism, and this reaction is also called the Wittig reaction. I don't know why, but it is. And usually ylids are simple molecules, but the only important factor is that there is a negative charge directly connected to a positive charge, and so this makes this molecule very reactive. And typically an ylid has a triphenylphosphine group on it, and that would be this group right here that we'll be using. But essentially, to help explain this a little better, we have our ylid right here with our negative and our positive charge, and we have our carbonyl group right next to it. And because our ylid has a dipole moment and our carbon has a negative charge, the electrons on the carbon will act as a nucleophile, and those electrons will attack the backside of the carbonyl group, moving the electrons from a double bond connected to the oxygen up to the oxygen, and that will form a somewhat cycloaddition reaction. So I'm going to erase a little bit of it just to show it a little bit better, but this is what we get after the nucleophile attacks. It forms this bond right here, and because we now have a very unstable molecule, and we have to deal with this positive and negatively charged atoms, this molecule will undergo cycloaddition. So the bond between the phosphorus and the carbon right here, those electrons will move down to the carbon-carbon bond. That will form a double bond. And then, because this carbon now will have an extra bond on it, it will be positive. So then these electrons right here connecting the carbon and the oxygen will move to connect the oxygen and the phosphorus, which weren't originally connected. So I'll erase a little bit of this, just to preserve it. And then moving forward, we've now disconnected the phosphorus group and the oxygen, and we've now formed a double bond between the carbon. So this is our product right here, and this is kind of our byproduct. So the triphenylphosphine is basically this right here, and sometimes it's abbreviated with the 0 or an O, a 3, and then a P, and then this is the double bond to the oxygen right here. So basically, the triphenylphosphine is a really good activator, and it can easily make an ylide. So I think now let's talk about how we make the ylide. So like before, we have our triphenylphosphine. It has 3 bonds connected. Well, I guess the phosphorus has 3 bonds connected to it with 2 electrons on it, meaning that it can serve as a nucleophile. And so this nucleophile will always attack it's usually a primary alkyl halide, but an alkyl halide because the halide, especially bromine, is a really easy leaving group, and the phosphorus, or the electrons on the phosphorus, can easily attack the carbon connected to the bromine because of sterics. So that's why we don't really use sterically hindered alkyl halides, and we'll use primary ones instead. So anyway, the nucleophile will attack the carbon, making the bromine leave. The bromine leaves, and now we have a bond connecting the phosphorus and the carbon, and the phosphorus now has a positive charge because it has an extra bond on it. Okay, and then to help stabilize this a little bit, we are going to use our, I think it's butyl lithium, and this molecule will separate into respective ions, and the butyl group will take the hydrogen's electrons move to the carbon, and we will end up with a negative and a positive charge right next to each other, and this is our ylide. And if we wanted to stabilize this more, we would move these electrons from the carbon down to form a double bond, and taking away that positive charge on our phosphorus. So there you go. That's how you make an ylide. Very useful, especially for the Wittig reactions when you're wanting to change a carbonyl group into a carbon-carbon double bond. All right. So next, let's talk about nitrogen nucleophiles. Nitrogen nucleophiles will form enamines or imines. If your nucleophile is a primary amine, it'll form the imine product, or if your nucleophile is a secondary amine, it'll form the enamine nucleophile. So looks like we're starting with our enamine product formation. So that means we need to start with a nitrogen nucleophile. So right here you can see we have our nitrogen. I'm going to change colors here. We have our nitrogen. It's connected to 2 carbons, making it a secondary amine. Because our nitrogen has electrons on it, it will attack the delta positive side of the carbonyl group. It will attack from the back, moving the electrons up from the double bond into the oxygen, forming not only an unstable nitrogen group, but also an unstable oxygen group. And then next, something that's important to remember is nitrogen nucleophiles work best in slightly acidic environments. So I wrote proton in excess here just to like represent the acidity of a solution, but also two things kind of happen at once here. So the nitrogen is positively charged, meaning it has an extra bond on it, meaning that it needs to get rid of the hydrogen group attached to it. So the hydrogen will leave, and then as this hydrogen is leaving, this oxygen can either take the hydrogen from there, or it can take a hydrogen from the environment. I think either works, but essentially it keeps doing that until it forms a good leaving group. And we know that our OH leaving group is not a good leaving group, but we know a water leaving group is. So that's what we want to make. So once we have a water molecule, that will leave the molecule, forming a positive charge on this carbon right here. And because that is now positive and unstable, our nitrogen group with its extra electrons will form a double bond to compensate for the positive charge. So we will have something that looks like this. And this is all fine, but the nitrogen is again unstable, it's positive. So we need to get rid of a bond. So to change this, we will do a hydride shift. Okay, and then our hydrogen bond will basically move from here to here, and then our double bond will move over one, and we'll get this hydrogen here. This is our enamine molecule, formed from a secondary amine nucleophile. Alright, next, let's talk about how we make an imine product. So to make this, we need to start with a primary amine nucleophile, and we have this right here below. I'm going to use a color highlighter so we can kind of see where I'm pointing. This is our nucleophile, nitrogen attached to one carbon group here. It has electrons on the nitrogen, meaning these electrons can be moved, and so the electrons will attack the delta positive side of our carbonyl group right here. These electrons will move up to the oxygen, and we'll get this. So now our nucleophile is attached to our carbonyl group. Our oxygen group is unstable because it's negative, and our nitrogen group is also unstable because it formed that bond with the carbon, making an extra bond attached to the nitrogen. So the nitrogen will be positive. And now, to help stabilize the nitrogen is going to kick off one of its hydrogens to stabilize itself, and then meanwhile this oxygen can take that hydrogen that was just kicked off and form an alcohol. Okay, so we have this now. And then we discussed this previously, but the OH group on the carbon is not a good leaving group. We need to turn that into a water group. So we'll use a hydronium ion, and this is okay because nitrogen nucleophiles work best in acidic mediums. So this oxygen will take the hydrogen from the hydronium ion, and the electrons from the oxygen will go, the electrons from the hydrogen bond will go to the oxygen. Okay, and then we will have water connected to our carbon. Water is a good leaving group, so water wants to leave. And then once that water leaves, this carbon will be positive because it's missing a bond. So to compensate for this, like we did before when we were forming the enamine, the electrons from the nitrogen will move to form a double bond connected to the carbon. And we will get this. And that's fine, except now the nitrogen is unstable, so we need to lose a bond. So we will use water from either the environment or as a product of the hydronium molecule that we just took a hydrogen from. We'll use water. The electrons on the oxygen of the water will take a hydrogen. Those electrons from that bond will move back to the nitrogen, and we'll have a stable molecule. This is our amine, formed from a primary nitrogen nucleophile. Alright, moving on, let's talk about oxygen nucleophiles. So I will be doing this portion of the video in purple just to help compartmentalize all of our notes here, our lovely notes. Okay, so for starters, I think it's important to differentiate the different products that we'll be making. So this is a hydrate. The hydrate has two OH groups connected to the same carbon. Okay, so hydrate. Then we have our semiacetal, and we have only one OH group, and then I think it's more of an ether group, so yeah, we'll call it an ether group. And then we have finally our acetal that has two ether groups. Okay, so that's that. First, let's talk about acid-catalyzed hydration. So in hydration, we will be forming our hydrate with our two OH groups connected to the same carbon, and we'll always start with the carbonyl group. So we have our carbonyl right here, and we have our acid in the form of a hydronium ion, and the oxygen on our carbonyl group will take a hydrogen off of our acid, could be a hydronium ion, and then it will form a very unstable oxygen because this oxygen now has an extra bond and it's positive. So we can use a water group because we want to hydrate. We can use our water group as a nucleophile, and then this nucleophile will attack the carbonyl group from the back side. It will move the electrons from the double bond up to the oxygen, and that will form a stable alcohol. And then this group in green right next to the alcohol is our water group nucleophile. And if I didn't say this already, in a hydration reaction, our nucleophile is always going to be water. It just might be acidified because this is acid-catalyzed hydration. So just a correction, we probably could use H2SO4 in this reaction, but I think it makes the most sense just to stick with hydronium and water. Alright, so we have our unstable oxygen molecule here, and we can use water to take a hydrogen from the oxygen, move the electrons down to the oxygen, and end up with a hydrate. Hydrate has two hydroxide groups connected to the same carbon. Alright, now let's talk about base-catalyzed hydration. We will start with a carbonyl group, like we always do, and instead of having like a hydronium ion, we will have a hydroxide ion, which is basic and negative. So this nucleophile will attack the carbonyl group from the back side because the back side is positive. The electrons will move up to the oxygen group, and that will form an unstable oxygen because it's now negative. And we already have our alcohol group, and this obviously happens faster than our acid-catalyzed hydration because basically here we need to take away a hydrogen or add a hydrogen, or etc. So we have our alcohol group and our unstable oxygen, and then all we have to do next is do a proton transfer and use water so that the oxygen on our molecule can take a hydrogen and turn itself into an alcohol. So this is our hydrate again. One thing to remember between acid-catalyzed hydration and base-catalyzed hydration is that the product of acid-catalyzed hydration will be an acid. So this is hydronium. And then the product of base-catalyzed hydration will be a base. Okay, so that's that. Next, let's talk about hemiacetal formation. And like I explained before, we have our hydrate, which is an oxygen connected to hydrogen, or two hydrogens, because we're using water as a nucleophile. But to create hemiacetals or acetals, we will use water, except instead one of the hydrogen has been replaced by an R group. So we'll see that, we'll see how we use that as we continue. But first, to move on from, but first to create an acetal, we have to make a hemiacetal. So as usual, we will start with a carbonyl group, and we will use our nucleophile and an oxygen connected to a hydrogen and an R group now. And then to activate our nucleophile, we can use an acid to add on a hydrogen and to make the oxygen positively charged, making it uncomfortable and more willing to react. So this oxygen will take a hydrogen from the acid, become positive here, and so now the electrons on our carbonyl group will want to take that hydrogen off of our modified nucleophile, and then we will have our oxygen will be positive now, and so because our oxygen is positive, this side, we need to change this, so we need to be able to move our electrons up to the oxygen to change the positive to a neutral oxygen. So basically, our nucleophile has permission to attack the carbonyl group from the back, moving the electrons up to the oxygen, forming an alcohol stable group. And then this group right here is our nucleophilic group that was just added, and this is unstable too because the oxygen is positive. So we need to take away a bond, and we can do this by using a base, and I represented that using an A with a negative charge. So this A can take the hydrogen from our nucleophilic group. These electrons will move back down to the oxygen, and we will have a hemiacetal. Okay. Yep. Hemiacetal because we have one OH group and one OR group connected to the same carbon. Okay. Finally, we have the acetal formation mechanism. And just as a review, a hemiacetal has only one OR group. Our acetal has two. You can think of hemi as half. So to make an acetal, you can either go through the entire mechanism to make a hemiacetal and then start, or you can just start with a hemiacetal. So we are just going to start with the hemiacetal. And then we have this. Okay. So because an acetal has two OR groups, we need to get rid of our alcohol group eventually. And to do this, we need to make the oxygen uncomfortable by protonating it. So these electrons from the oxygen will attack a hydrogen, making it a water group. Water groups are really good leaving groups. So that means the water will leave, this carbon will become positive, and then because this carbon is positive, these electrons from the OR group, one set will move down to form a double bond to help compensate for this positive charge. So we'll get this. And this is essentially an activated carbonyl because our carbonyl compound is charged and willing to interact with nucleophiles. So because our positive charge is on our oxygen, we need to do something to move these electrons up to the oxygen. So our nucleophile, again, given permission to attack the electrophile, moving the electrons from the double bond up to the oxygen, creating an OR group like we wanted, except now our nucleophile group, which is now attached to our molecule, is unstable because the oxygen is positive. So like before, I used the base, the A minus base, to take a hydrogen. Take a hydrogen and just make our acetal. Okay, that is it.